Modern computing is defined by the need to resolve millions of simultaneous, overlapping constraints in fractions of a second. In machine learning, this involves adjusting vast arrays of interconnected numerical weights to minimize an error rate. For telecommunications, it means calculating the most efficient path for massive data volumes without exceeding bandwidth limits. Modern cryptography secures this data using precise, reversible mathematical operations to encode information. And rendering computer graphics requires calculating the exact coordinates of millions of polygons for every single frame on a screen. Beneath all these fields lies a single classical mathematical framework: systems of linear equations. To solve massive optimizations efficiently, modern computing relies on translating algebraic constraints into highly structured data models. A system of linear equations is a collection of two or more equations that involve the exact same variables. The goal is to find a simple set of variable values, like x and y, that satisfies every equation in the system simultaneously. For an equation to be linear, it must follow strict rules. First, variables can only exist to the first power. This diagram shows a valid linear equation: 2x plus 3y equals 5. There can be no nonlinear terms, like a variable squared, a square root, or multiplied variables. In the equation x squared plus y equals 3, the exponent makes it nonlinear. Enforcing these linear constraints ensures predictable geometry, which is why computers can process them by the millions. Human-readable algebra, using letters, plus signs, and equal signs, is inefficient for programmatic processing. Consider this two-equation linear system: 2x plus y equals 5, and x plus 3y equals 6. To solve this at scale, we must strip away the algebraic syntax to reveal the raw numerical architecture. We remove the x and y variables, the addition signs, and the equal signs, leaving only the floating numbers. These numbers then lock into a rigid rectangular grid. This structural data model is known as an augmented matrix. A vertical boundary line separates the matrix into two distinct data categories. On the left are the coefficients, which are the multipliers of the hidden variables. On the right are the constants, representing the target numerical outcomes. By organizing the data this way, the augmented matrix transforms algebraic problem-solving into geometric data manipulation. We manipulate this matrix to simplify the numbers without changing the underlying mathematical truth of the system. The step-by-step method used for the simplification is called Gaussian elimination. The goal of this algorithm is to reach a layout called row echelon form, or REF. In REF, the leading coefficients in each row must be a 1. These are our pivots. Any number directly below a pivot must be eliminated and turned into a 0. We achieve this state using three specific elementary row operations. First is row swapping, where we exchange the positions of two rows. Second is row multiplication, scaling an entire row by a non-zero number. Third is row addition, where a row is replaced by itself plus a multiple of another row. Once Gaussian elimination achieves row echelon form, the values for the variables can be easily identified using back substitution. There is an alternative framework for solving the system, one that bypasses row-by-row reduction. We can treat the entire multivariable system as a single equation: a times x equals b. Here, a is the coefficient matrix, x is the variable matrix, and b is the constant matrix. We map the original numbers from our example into this structural formula. Normally, we would isolate x by dividing by a, but in matrix algebra, division does not exist. Instead, we find the inverse of matrix A, denoted as A inverse. Multiplying both sides by A inverse cancels out matrix A on the left side. This leaves us with an isolation formula: x equals A inverse multiplied by b. Direct matrix multiplication then provides the exact values for our unknown variables. The matrix inverse method shifts solving from row-by-row reduction to direct data multiplication, a process modern graphics hardware performs billions of times per second. We have mapped algebraic equations into matrix structures and solved them using two distinct mathematical paths. This path shows an augmented matrix moving through elementary row operations to reach row echelon form. The second path uses the coefficient matrix and an inverse calculation for direct multiplication. Both pathways converge on the exact same coordinate solutions. This exact mathematical resolution is precisely what allows modern software to optimize complex networks and render detailed digital worlds. Whether through Gaussian reduction or calculating an inverse, manipulating these linear data structures is the fundamental requirement for modern computational logic.